Bone scanning requires technetium 99 metastable. It's the radioactive tracer, and it's combined in this case with phosphate. As bone takes up calcium and phosphate, that's what it's primarily made of. The use of technetium 99 in an amalgam with that, or combined with that methylene diphosphate, is what's used. Okay, it goes through the blood and it's incorporated into the bone. Remember that. Okay. Then the patient lies under a gamma camera, and the gamma camera comes, as you'll see on the next slide, detects the radioactive tracer in the body. The gamma rays are given off, and they pass up through sodium iodide detectors with small amounts of thallium, and it counts those that come directly up each tube, and you'll see that on the next slide. When that flash of light is detected as the gamma photon enters the detection tubes of the gamma camera, the signal is faint, but it's multiplied by a photocell or photomultiplier, which then sends a signal to the computer. It can be displayed on a screen, or it can be then saved as data and stored as digitally encoded material. But the main things to look at here: the phosphate, the technetium 99, gamma camera consisting of these sodium iodide crystals with a little bit of thallium, and then the signal from each gamma ray hitting those tubes produces an electric signal which is stored digitally. Here we have two images. The one on the right is an X-ray. You can see it's very structural. You can't really see some of the bones in behind here, as there's bones next to or overlapping other bones. And we've got some ghosting here, or the person has two thumbs. Some minor movement or soft tissue that's there in between. There's something here that I'm not really sure what that is. So we can see basically what we're looking at. What's been absorbed by the X-rays did not get through to the film. The film wasn't exposed, so when the film is developed or reversed, you'll see white in those areas that X-rays were absorbed in. On the left we have a bone scan. It looks a little bit like a PET scan, but it is different. In this case, it's not done with positrons. It's done using technetium 99 metastable. And that technetium decays to form a more stable form of technetium, which is a beta emitter, but that does not emit above background radiation levels. So we don't worry about that. This is the one we want, but when it decays, it produces a gamma ray. So a gamma camera can detect those areas that are producing more of the, have absorbed more of the technetium. Now, if you have a break in a bone, calcium and phosphorus are going to be absorbed by that bone. Same thing happens if you have a tumour. It's absorbing. If it's a fast-growing bone, it's absorbing calcium and phosphorus. So your technetium amalgam with phosphorus included is taken into the bone more quickly. So we can see here an area on the bone scan where more of the phosphate combined with technetium 99M is absorbed into the bone. So there's something going on here in the bone. It could be a break, it could be an arthritic condition, it could be a tumour or some other condition. As you can see on the X-ray, it didn't really show up. There's some slight circular material there. There's something here, but it's not very clear. Whereas on the bone scan produced from our technetium, it's very clear. This is a diagram of the gamma camera. You can see we have these collimators, which is just a tube that only accepts photons directly from below or at 90 degrees to the patient. Other photons at angles are absorbed by the lead, so they don't travel up the tube, they travel in and are absorbed. So it's a good way to identify exactly where these gamma photons are coming from. So the radioactive source in the body might be here, and those collimators, or long thin tube with a hole at the bottom. Up the top we have our detector, our sodium iodide crystals, and here we have multipliers that take that little flash of light when a gamma ray comes up, flash. They take that light and transfer it, multiply it, make it bigger. It's processed by a computer, then sent to a screen. It is also stored digitally for later analysis. Now, those areas that produce more gamma rays will have more light, have a greater signal, and will turn up more on the gamma scan or the bone scan. So here we're using phosphorus-based, and you can see here we've got bones, fractures, arthritis, things, and cancer that will show up. This circle here on the scan is caused by the injection of the material, our TC, and our phosphorus amalgam. Here we have some patients' bone scans. The first two are healthy scans. There's some, maybe some accumulation of the technetium amalgam, phosphate amalgam in the bladder, so that would probably have to be investigated by a diagnostician. These two here, we have the patient lying on their back and here lying on their stomach. These two are where the injection site was for the technetium phosphate amalgam. So these two are healthy, as you can see here. The end person is a separate scan, and you can see possibly the site, but the other site you'll also have variety, and I'm just putting some spots on areas that are releasing a lot more gamma rays to the gamma camera, so they're more highly exposed. Instead of appearing very white and the rest is dark, the image is reversed. So those areas that are producing more gamma rays are considerably have a greater level of technetium phosphate absorbed into the bone. So there's something happening in the bone of those patients. Now this patient was a breast cancer patient, and the cancerous metastases or finger-like projections of the cancer have grown into the bone, and they're growing through the bone and spreading in this patient. So not a good prognosis for that person, but a bone scan clearly shows the areas that have been absorbing more of the technetium. Further investigation can take place here with X-rays, just to determine what sort of tumours are spreading in the bone. And the final image here is again same sort of thing. And these two images, we'll just consider this one. And you can see the metastases have spread into the bone, liver or kidneys, and glands, and you can see quite a few. And that's showing up as on our bone scan. Remember, a bone scan uses gamma emitter, technetium 99. M. Don't forget the M, Metastable. It's the version that produces this. It has a half-life of 6 hours, and it's milked from molybdenum. And the technetium is the byproduct of that. So it can be stored in hospitals, in shielding. The technetium's taken out. It has a half-life of 6 hours. It does form another form of technetium in the body, which is not metastable, but it is a lower emitter, and it doesn't produce more than background emissions of beta particles.